Hi, Chem 112 students. This is Lesson 20-2, Part 2. We're going to talk a little bit about acid strength and how that structure of the acid will affect that. So molecular structure will affect the acid strength because an acid wants to lose a proton. Acids donate a proton. So if your base, your conjugate base, is chloride or acetate or nitrate or fluoride or whatever it might be, we're still saying how easily does that proton break away from that conjugate base. If it's a weaker bond, you're going to be able to pull that proton off more easily, and it's a stronger acid. So we need to know what HX bond strength depends on, and there are two different trends that you need to know. For the binary acids, binary means that you're combining proton directly bonded to one element. So HF, HCl, HBr, and HI all have a bond directly to that proton. In this case, we can just look at the bond enthalpy. That tells you about the bond strength. You can see that HF has the largest bond enthalpy. It's a very strong bond. It's hard to pull that proton off. And therefore HF is a weak acid. It's not one of our 7 strong acids. HCl, HBr, and HI are all strong acids. In fact, they're equally strong in water because they're all completely deprotonated. They're ionized. That proton has come off completely. If we were to put those 3 acids in a non-aqueous solvent, we would be able to tell a difference in the strength of them by looking at the bond strengths. Since HI is the largest atom, it has the longest bond and has the weakest bond. So in non-aqueous solution, HI would be the strongest acid. But again, those 3 acids are all completely ionized in water and are equal in strength. For the non-binary acids, you're going to look at a different trend to tell about that HX bond. When I say non-binary acids, usually X is equal to oxygen, and the acid would be called an oxyacid. Y would be some other group of atoms. If X is very electronegative, like an oxygen, it has a lot of electron withdrawing power. That polarizes that bond to the hydrogen and makes it a stronger acid. It's easier to transfer that proton away to a different conjugate base. The bond breaks more easily the more electronegative that X atom is. Down below, if X would be equal to carbon, and the hydrogen is bonded directly to a carbon, that's a more covalent bond. They have similar electronegativity, and they share their electron density more equally. It's a stronger bond. It's very neutral. So CH bonds, which are nonpolar, are not acidic. It's going to be difficult to break those in solution. So it all is going to depend on the electronegativity of that element there. The trend could be summarized here. Acid strength is going to get bigger and increase the more polarized that bond is to the proton. These are 2 different oxyacids, and I want to remind you about the trends for electronegativity. So if we're going up a group on the periodic table, going to get more electronegative. In other words, you're moving closer to fluorine, which is the most electronegative element. So F would be first, then oxygen, chlorine, nitrogen, and then a bunch of other elements. But it would be good if you could remember these 4 in order, with fluorine being the most electronegative. How about moving across a period from left to right? Again, you're going to have electronegativity increase. So don't forget how to tell what is more electronegative. The closer you are to fluorine, the more electronegative you are. In fact, you can say that electronegativity is the ability to attract electrons within a bond. It's not electron affinity. It's not gaining extra electrons. It's just attracting them to itself within that bond. So these are oxyacids. They're not binary acids. And oxygen is very electronegative, more so than chlorine or bromine is going to be. In the HOCl case, it's got a higher positive charge. This blue number is the amount of positive charge that's on that white hydrogen atom there. You can see the electronegativity differences, chi, in here, 3.44 for oxygen. But chlorine is higher in electronegativity, 3.16 versus 2.96. Therefore, the oxygen here is hungry. It wants more electronegativity, it wants more electron density, but chlorine doesn't want to give it up. So it has to get it from the hydrogen bond. Polarizes that hydrogen bond between chlorine and between the oxygen and the hydrogen. So the oxygen-hydrogen bond is more polarized in the top HOCl. There's less density in that bond. It's shifted. It has a positive charge on it that's bigger than the bottom acid, and it's more easily donated to water. That means HOCl is a stronger acid. If you were to look at the three different oxyacids, HOCl, HOBr, and HI, and put them in order, you would say HOCl would be greater than HOBr, which would be greater than HOI. And this follows electronegativity trends. This is true if the number of oxygen atoms is the same when you're comparing acids. If the number of oxygen atoms is different, you're going to look at the oxidation state of the central atom. Basically, the more oxygens you've got, the stronger the acid is going to be. You're going to have more electron withdrawing power. You could also say that the highest oxidation state has the strongest acid. So in HOClO3, we're going to have more electron withdrawing power because there's more oxygens here. It's a positive 7 chlorine oxidation state. And the next one is a positive 5 chlorine oxidation state. Over here we have a plus 3 chlorine oxidation state, and over here is a plus 1 chlorine oxidation state. So what we do is put greater thans for these 4 acids in like that. The more oxygens, the higher the oxidation state, the stronger the acid. This is true when the central atom remains the same. We saw a little bit before about resonance. And here again, the stability of the conjugate base is going to affect the acid strength. So this is a carboxylic acid that you may remember from Chem 110. Sometimes we write it H3CCOOH. The red proton is the acidic one, and if we pull that off, then we have resonance, where we can share electron density between more than 2 atoms. It's delocalized electron density, and that adds to the stability of that anion that it leaves behind. So the greater the ability of that anion to support a negative charge means that's a stronger acid. So delocalizing that negative charge increases the conjugate's stability, and that's a stronger acid. The better it can do that, the better it's going to be at it being an acid.